Hello students, let's continue with the numerical part of the chapter 15, Structure of Atoms and Nuclei. Before proceeding, just let's go through the important formulas that we will use here. First one, 1 upon lambda is equal to r in bracket 1 upon n square minus 1 upon m square. The detailed discussion we have done for all the formulas. Here we are just going through it. The value of RH we are taking by using the formula Me e raised to 4 upon 8c epsilon naught h cube. Then next, by using the Bohr's first postulate, mv square upon r is equal to ze square upon 4 pi epsilon naught r square, and hence in general it is to be given as me vn square upon rn is equal to ze square upon 4 pi epsilon naught rn square. By using the Bohr's second postulate, we are obtaining the formula Me Vn Rn is equal to n h upon 2 pi, and by using the third postulate we are having the formula h nu is equal to Em minus En. Then next, from the expression to determine the radii of the Bohr orbit, we are having the formula Rn is equal to n square h square epsilon naught upon pi me ze square. And the same we can write Rn is equal to A0 into n square, where A0 is nothing but h square epsilon naught upon pi m ze square there. Then the velocity of the revolving electron in any orbit can also be determined by using the formula Vn is equal to ze square upon 2 epsilon naught hn. The energy of the electron revolving in any orbit is to be given by the formula En is equal to minus me z square e raised to 4 upon 8 epsilon naught h square n square. And to make our calculation simple, we are using the another formula also, that is En is equal to minus 13.6 z square upon n square electron volt, where 13.6 electron volt is the value of Me e raised to 4 upon 8 epsilon naught h square there. After that, from the radioactive decay law, we are having Nt is equal to N0 e raised to minus lambda t, and in the same format activity, that is a disintegration per unit time or disintegration rate, activity At is equal to A0 e raised to minus lambda t. Then mean half lifetime is also to be determined by using the formula T half is equal to ln2 upon lambda, where it is to be given also as 0.693 upon lambda, as the value of ln2 is 0.693 there, and lambda is said to be the decay constant, and the mean life is to be related with the decay constant. It is inversely proportional to it, and hence it is to be given as mean life tau is equal to 1 upon lambda. And finally, here we can relate the half life time and the mean life by using the formula as T half is equal to tau ln2, and finally we can write it as T half is equal to 0.693 tau. Now let's proceed further. Example 15.1. Calculate the radius of the third orbit of the electron in hydrogen atom. In this question, it is given that the electron is revolving in the third orbit. Hence the value of n we have to take as 3, and we have to determine the radius of the third orbit of the electron in the hydrogen atom. Here we are using the very basic formula to determine the radius of the orbit Rn is equal to a0 n square. As we know that Rn is proportional to n square there. So the proportionality constant over here we are denoted by a0, and the value of a0 as we are having 0.053 nanometer. So let's substitute the values in this equation. Rn is equal to a0 n square there. As the value of n is 3, so it is to be written as R3 is equal to a0 into 3 square. 3 square is 9 into a0 is there. So 9a0 will become as a0 is 0.053 nanometer. It is to be multiplied with 9, and hence we are getting the multiplication as 0.477 nanometer. So this is the value of R3, that is the radius of the third orbit of the electron in the hydrogen atom. It is to be given by 0.477 nanometer. Next, example 15.3. Determine the energies of the first two excited states of the electron in hydrogen atom. What are the excitation energies of the electrons in these orbits? Over here, first of all, we have to determine the value of energy of the first two excited state of the electron in the hydrogen atom, and hence we have to determine the excitation energies of the electrons in these orbits also. Let's see the solution. The energy of the electron in the nth orbit, as we had derived the expression for the same also, is given as, in general, En is equal to minus 13.6 upon n square electron volt. The first two excited state we are having n is equal to 2 and n is equal to 3. The ground state is to be given as n is equal to 1. So after the first orbit, the next excited state will be the second orbit, and after that the second orbit, the next excited state will be the third orbit. That's why the first two excited state must be n is equal to 2, which is the first excited state, and n is equal to 3 is the second excited state. Let's determine the energies for these two excited states there. As we are having the formula En is equal to minus 13.6 upon n square electron volt, so E2 will be written as minus 13.6 upon 2 square electron volt, as the first excited state having the value of n as 2. Then this 2 square is 4, and we can write it as minus 13.6 upon 4. And after the calculation, we are getting the value of E2 is minus 3.4 electron volt. Next, we have to determine the energy for the second excited state, which is value of n is 3. So E3, as per the formula given as minus 13.6 upon 3 square there, and this 3 square becomes 9, and it will be written as E3, the second excited state, is equal to, having energy is equal to minus 13.6 upon 9. On solving, we are getting the value of E3 as minus 1.51 electron volt. Excitation energy of an electron in nth orbit is nothing but the difference between its energy in that orbit and the energy of the electron in its ground state. That is, we know that the energy of the ground state is nothing but minus 13.6 electron volt. Thus, the excitation energy of the electron in the first two excited state are to be calculated, and it is to be given as, for the first two excited state, as first excited state is given as n is equal to 2. Okay, so for this the value of energy we are having minus 3.4 electron volt, and here we have to take the difference with the ground state, that is minus 13.6 electron volt. So it is to be written as 3.4 minus 3.4 minus 13.6 electron volt. On taking the difference of these two values, we are getting the excitation energy for the first excited state is 10.2 electron volt. Similarly, to determine the excitation energy of the electron for the second excited state is the difference between E3 and the energy of the electron in the ground state. So the difference between E3 and E1 will gives the value of the excitation energy of the electron in the second excited state. So it is to be taken as minus 1.51 minus 13.6 electron volt. On taking the difference of these two, we are having the value 12.09 electron volt. So here we can conclude that the energy of the electron in the first two excited state, that is E2, is to be given as minus 3.4 electron volt, and E3 is to be given as minus 1.51 electron volt. And also the excitation energy of the electron in the first two excited state are to be given as 10.2 electron volt and 12.09 electron volt respectively. Now the next example 15.4, calculate the wavelengths of the first three lines in Paschen series of hydrogen atom. Over here, as we know that for the Paschen series the value of n is 3 and the value of m is 4, 5, 6, 7, etc. Here we have to calculate the wavelengths of the first three lines in the Paschen series. That means here we have to determine the wavelengths of the first three lines, which would be m is equal to 4, 5 and 6 in the Paschen series of hydrogen atom. Let's see the solution. As the wavelengths of the lines in Paschen series n is equal to 3 we are having, and hence by using the basic formula 1 upon lambda is equal to RH in bracket 1 upon n square minus 1 upon m square. So value of n for the Paschen series here we have to take as 3. RH is the Rydberg constant. We know the value is 1.097 into 10 raised to 7 per meter. Okay, so the formula will become for the Paschen series is 1 upon lambda is equal to 1.097 into 10 raised to 7 in bracket 1 upon 3 square minus 1 upon m square. Now we have to calculate the wavelengths of the first three lines in the Paschen series of the hydrogen atom. So the first three lines would be, the value of m is 4, 5 and 6 there. Then for the first three lines, as it will be value of m is 4, 5 and 6, let's substitute these values in the formula above, and the first line, it is to be denoted in the Paschen series as 1 upon lambda. 1 will gives the value of the wavelength of the first line in the Paschen series, and hence for this the value of m we have to take as 4. So the formula will become 1 upon lambda 1 is equal to 1.097 into 10 raised to 7 in bracket 1 upon 3 square minus 1 upon 4 square. Let's solve this bracket first. So we are having the value 7 divided by 9 into 16 there, and it is to be multiplied with 1.097 into 10 raised to 7. On solving this value, we are getting the value of 1 upon lambda 1 as 0.0533 into 10 raised to 7 per meter. As this is the value of the reciprocal of the wavelength of the first line, we have to determine the wavelengths of the first three lines. Okay, so here we have to take the reciprocal again. That means only we have to determine the value of lambda 1. We don't want the value of 1 upon lambda 1. So let's take the reciprocal of 1 upon lambda 1. So reciprocal of 0.0533 into 10 raised to 7 per meter we have to take. So it gives the value of the lambda 1 there, and lambda 1 is the wavelength of the first line in the Paschen series. And hence, on taking the reciprocal of 0.0533 into 10 raised to 7 per meter, we are getting the value of lambda 1 as 1.876 into 10 raised to minus 6 meter. Then next, let's determine the wavelength of the second line in the Paschen series. For that, the value of m is to be taken as 5. And the formula will become 1 upon lambda 2 is equal to 1.097 into 10 raised to 7 in bracket 1 upon 3 square minus 1 upon 5 square. On solving this bracket, we are getting 16 upon 9 into 25. That is to be multiplied with 1.097 into 10 raised to 7. On solving this multiplication, we are getting the value of 1 upon lambda 2, which would be 0.075 into 10 raised to 7 per meter. Again, this value is the value of 1 upon lambda 2. Hence, to determine the wavelength of the second line in the Paschen series, that is the value of lambda 2 is to be given when we are taking the reciprocal of 0.075 into 10 raised to 7 per meter. So the lambda 2 we are getting as 1.282 into 10 raised to minus 6 meter. After determining the wavelength of the second line in Paschen series, let's determine the wavelength of the third line in the Paschen series there. And for the determination of the wavelength of the third line in the Paschen series, the value of m we have to take as 6, and the formula would become 1 upon lambda 3 is equal to 1.097 into 10 raised to 7 in bracket 1 upon 3 square minus 1 upon 6 square. On solving this bracket, we are getting 27 upon 9 into 36 there, which would be multiplied with 1.097 into 10 raised to 7. And on solving this, we are getting the value of 1 upon lambda 3 as 0.0914 into 10 raised to 7 per meter. And this value is the value of 1 upon lambda 3. Hence, to determine the value of lambda 3 only, we have to take the reciprocal of 0.0914 into 10 raised to 7 per meter there. And finally, we are getting the value of lambda 3 as 1.094. The value of lambda 3 as 1.094 into 10 raised to minus 6 meter. So here we have calculated the values of wavelength of the first three lines in the Paschen series of hydrogen atom. The wavelength of first line in the Paschen series we are getting as 1.876 into 10 raised to minus 6 meter. The wavelength of the second line in the Paschen series we are getting lambda 2 is equal to 1.282 into 10 raised to minus 6 meter, and the wavelength of the third line in Paschen series we are getting lambda 3 as 1.094 into 10 raised to minus 6 meter. Now the next unsolved numerical we have from the textbook, question number 22. Before the year 1900, the activity per unit mass of atmospheric carbon due to the presence of carbon-14 averaged about 0.255 becquerel per gram of carbon. A. What fraction of carbon atoms were carbon-14? B. An archaeological specimen containing 500 mg of carbon shows 174 decays in 1 hour. What is the age of the specimen, assuming that its activity per unit mass of carbon when the specimen died was equal to the average value of the air? Half-life of carbon-14 is 5730 years. Now here, in this question, we have to determine the fraction of carbon atom which was present in carbon-14, and also we have to determine the age of the specimen used there. Let's see the solution for this numerical. As it is given, before the year 1900, the activity which is to be given as 0.255 becquerel, that is, we can say that the magnitude of dNt upon dt is 0.255 per second there. And also the half-life is given 5730 years. Here we are going to convert the half-life of carbon-14 atom is from years to second, and for this we have to multiply the factors with 5730. Over here we are going to multiply with 365, then 24, then 60, and again 60 to make the half-life time from years to second there. And after the multiplication of 5730 into 365 into 24 into 60 into 60 will be around 1.81 into 10 raised to 11 second. Hence, the disintegration constant we can determine by using the formula lambda is equal to 0.693 upon T half, where T half we are getting as 1.81 into 10 raised to 11 second. So that the disintegration constant lambda, we are having the ratio 0.693 upon 1.81 into 10 raised to 11. And this ratio we are getting as 3.83 into 10 raised to minus 12 per second there. The total number of radioactive carbon atom in 1 gram we have determined by using the atmospheric carbon, that is Nt is equal to the ratio we are getting as dNt upon dt divided by disintegration constant. As the value of dNt upon dt we are having 0.255 per second, and disintegration constant we are getting as 3.83 into 10 raised to minus 12. So we can get the total number of radioactive carbon atoms in 1 gram, that comes around 6.66 into 10 raised to 10 per gram. The number of carbon atoms available in 1 gram of carbon can be calculated by using the formula, which is to be taken as the ratio of Na upon m, where Na is the Avogadro's number, Avogadro's constant, and m is the molecular mass of the carbon. And hence, by considering these values, we can get the number of carbon atoms available in 1 gram of carbon. As Na is 6.022 into 10 raised to 23 and molecular mass capital M of the carbon is 12, so we are getting the value of Nc as 5.02 into 10 raised to 22 per gram. And hence finally we are getting the fraction of radioactive carbon in 1 gram of atmospheric carbon. And that fraction that we have to calculate for the carbon atom is to be taken as the ratio of N upon Nc. As N we have calculated also, which is nothing but the total number of radioactive carbon atoms in 1 gram, and Nc also we have calculated, which is the number of carbon atoms available in 1 gram of carbon. So over here let's substitute the values. As N we have got the value 6.66 into 10 raised to 10, and Nc we are getting as 5.02 into 10 raised to 22. Let's solve it by using the log calculation. As 10 raised to 22 in the numerator becomes 10 raised to minus 22, and 10 raised to 10 into 10 raised to minus 22 will give the value 10 raised to minus 12. So this factor we are keeping aside. The remaining factor is remaining 6.66 upon 5.02. Let's solve this by using the log calculation. As we are applying log, so we have to first of all write down the anti-log of 6.66 upon 5.02. The formula log A upon B is nothing but log A minus log B, so that it is to be written as anti-log of log 6.66 minus log 5.02, and out of the bracket we have to write 10 raised to minus 12, which we are keeping as it is. Let's write down the value of log 6.66 and log 5.02, and let's do the subtraction of these two values. And out of the bracket here we have to simultaneously write down anti-log also. So the subtraction of these two values we are getting as 0.1228, and hence let's see the anti-log of 0.1228 over there, and into 10 raised to minus 12 we have to write down simultaneously. The value of anti-log 0.1228 we are getting as 1.326, and the factor 10 raised to minus 12 we have to write over there. Then we are getting the reciprocal of 1.326 into 10 raised to minus 12, which we are obtaining around 0.75 into 10 raised to 12. That means
One atom is radioactive in every 7.5 into 10 raised to 11 atoms. And hence, by considering the standard conventions of expressing quantity with appropriate order of magnitude, there were 4 radioactive atoms in every 3 into 10 raised to 12 carbon atoms. Now next, let's determine the age of the specimen. As 174 decays per hour is shown for 500 milligram of carbon atom, and hence here we can say that 348 decays per hour will be takes place for 1 gram, and therefore for 348 decays per hour that will take place for 1 gram, we can convert it into decays per second also. So 348 is to be divided by 60 into 60, and hence we are getting the value decays per second per gram there. And the value comes to us 0.097 decays per second per 1 gram. For the age of the specimen, here we have to use the formula T is equal to 2.303 upon lambda into log A0 upon AT. As the lambda we have determined, value we are getting as 3.83 into 10 raised to minus 12, and A0 is given to us 0.255 becquerel, and AT is given over here that we have calculated 0.097 decays per second per 1 gram. So substitute the values over here and let's solve it to determine the value of T, which gives the age of the specimen. So when we are solving 0.255 upon 0.097, we are getting 255 upon 97 only, and hence let's solve this much by using the log calculation. So it becomes your log 255 minus log 97 there. Let's take the, as here we have to take the log of this ratio. So it becomes log 255 minus log 97. Let's take the value of log 255, which comes to us 2.4065 minus as it is, and the value of log 97 is 1.9868, and the other values for 2.303 upon 3.83 into 10 raised to minus 12 we are writing simultaneously as it is. At this step, where we are getting 2.303 upon 3.83 into 10 raised to minus 12 into 2.4065 minus 1.9868. Here let's do the subtraction of these two values and solve by using this factor. So here we are getting the value of T as 2.524 into 10 raised to 11 second there. Let's convert the value of this time from second to years there, and hence here we have to divide by the multiplication factor of 365 into 24 into 60 into 60. After calculating this value, we are getting the value of time, which is nothing but the age of the specimen comes around 8003 years there. So here we have got, first of all, there were the 4 radioactive atoms in every 3 into 10 raised to 12 atoms were there in carbon 14, and age of the specimen here we are getting is around 8003 years there. So students, you have to solve and practice all the numericals. Thank you.